I am really happy to introduce Zhe Peng. Zhe is currently a research scientist at Ceres and the Department of Chemistry at CU Boulder. He received his PhD in physical chemistry from the University of Paris, Saclay in France. And since 2014, he has been working mainly as a box modeler in the group of Jose Luis Jimenez at Ceres. And his research interests include investigation of volatile organic compound oxidation and aerosol formation in both the atmosphere and lab experiments, using both parameterized and fully explicit models. In this case, GECKO-A, and as you can hear from this presentation. I really appreciate Zhe that you are presenting today, and go ahead and thank you.
Thank you for the introduction, Ivan. Today, I'm going to present some of my work in collaboration with the GECKO team at NCAR. I'm going to talk about the evolution of ultra-activity in low NO volatile organic compound photooxidation. First, I'd like to thank all my co-authors and the founder, NSF. Probably most of you are very familiar with this scheme of VOC oxidation and aerosol and ozone formation. The very first step of this scheme is the reaction of VOCs with OH. So OH is indeed a central driver of atmospheric chemistry. OH reactivity governs OH loss. It is the sum of the products of reactant concentrations and their reaction rate coefficients. It provides constraints on OH lifetime and budget. Despite its importance, it's not well constrained. This perspective paper by Williams and Broom pointed out several things that need to be addressed in OHR research. First is there's significant missing ultra-activity, which is the part of ultra-activity unaccounted for by the chemically speciated components. And this missing reactivity cannot even be recovered by model as explicit as MCM. And the third point is OHR research is really needed for clean remote regions where NO is very low and photochemical ages are high. To address these points, we use the fully explicit GECKO model to study the OHR evolution in the low NO photooxidation of alkenes, alkene, and aromatic species until very high photochemical ages. But the current model the current version of GECKO doesn't include auto-oxidation of R2, but a new version that includes auto-oxidation is being developed. Once it's finished, we are going to use it and look at the results again. With this version, we studied OHR evolution in different environments: atmosphere, large Teflon chamber, and an alternative to chambers that can reach very high ages. That is oxidation flow reactor. If you are interested in more detail about OFR, you can refer to this review paper we published in Chemical Society Reviews earlier this year. In case some of you are not familiar with GECKO, I'll briefly introduce it. I copied 2 slides from Julia. So simply, a GECKO is a computer program that automatically generates oxidation scheme using experimental data and structure activity relationships. It can identify oxidation pathways and estimate kinetic data such as rate coefficients. It starts with the precursor and scan for every species involved till everything goes to CO2. It can deal with both VOCs and radicals. The radicals it can treat it include alkyl proxy radical, isoproxy, and alkoxy. For VOCs with CH bond, it considers OH reaction. With those with CC double bond, it considers ozonolysis and NO3 reaction. And those with CHO group, it considers its NO3 reaction. And for other functional groups, GECKO consider their photolysis and thermal decompositions. And for some special types of precursors, GECKO can't use existing structure activity relationship to write their mechanisms. For example, for aromatics, this aromatic m-xylene. So it takes the scheme from MCM, in this case for initial m-xylene oxidation. But MCM scheme is mainly for high NO chemistry. So at low NO, some species in the scheme may be left as dead end because they only react with NO. But to avoid that, the scheme is extended for low NO oxidation with a lot of help from John. We are also aware of several numerical issues in the GECKO solver. The first one is the integration time step issue. We did some test runs to select properly the integration time step, except the run shown here. In all other runs, the outputs converged properly as we decrease the time step. So we can find a good time step for integration. And for this run, an Isoprene OFR run, the outputs fluctuated within a narrow range as we decrease the time step, but the fluctuation is very small. Considering other sources of uncertainty, we think this is okay. So we take the time step for the carbon atoms in the GECKO solvers in our study is minor.
Hi, Zhe. I think the connection is not really great.
Hi.
Hello. I think
Hello?
the connection is... Zhe, can you hear me?
Hello?
If you
Yeah,
want to turn
you.
your camera off, that will be great because the connection sometimes is not really great. Let's try it to see if it improves.
Yeah,
Okay,
I turned my
perfect. Can
camera
you
off.
just go back to your presentation mode, please? Thank you. Sorry.
Yes. No problem. To facilitate output analysis, post-processing, and graphic making, with the a huge amount of complex GECKO output data, we also made development of the GECKO loader and plotter led by Harvard in Igor Pro. It can easily load a large amount of net CDF and ASCII outputs from GECKO and make this graph easily. So we can do result analysis in a visual and interactive way with this GECKO loader. Now let's look at the results. I'll start with the simplest case, a simple oxidation chain. For such a simple chain, at steady state, the reactive fluxes of all reactants are equal. Then all OH reactants contribute equally to the total OH reactivity. We can apply this ideal case to a hypothetical case of methane oxidation without R2 plus R2 or organic photolysis. If we remove these reactions, methane oxidation does look like a simple chain. And in the middle is the result. The y-axis is OH reactivity, and the x-axis is OH exposure. So it shows the evolution. And you can find in the red axis the corresponding equivalent photochemical ages to the OH exposure. Because methane reacts very slowly with OH, the system can reach the steady state, and the total OH reactivity goes up substantially before reaching the peak around 2 months of aging. And after that, everything goes down because methane starts to be significantly consumed. At steady state, you can see the contribution from methane, formaldehyde, and CO are roughly equal. But that from methyl hydroperoxide is much larger because in the mechanism, methyl hydroperoxide can also react with OH, producing back to methyl peroxy radical. This is not part of the chain, but it also contributes to OH reactivity. If you look at a more realistic ambient case, the total OH reactivity is much lower because now we have R2 plus R2 and organic photolysis. These reactions also make the oxidation proceed, but they bypass the OH reactions. So they don't contribute to OH reactivity. Now let's look at the result of oxidation of a VOC of more interest, which is Decane. Let's start with the ambient case. Well, the results of 2 ambient cases, diurnal cycle and constant sunlight, but they look almost the same. So from now on, I only refer to the constant UV case for ambient cases. If you look at the curve of the via attractivity evolution in decane oxidation, you can find a lower peak at lower age compared to methane oxidation. To figure out why, let's look at the detail of this oxidation. First, we start with precursor decane. It decays much faster than methane. But its first generation oxidation product, C10 hydroperoxides, are more reactive than decane itself. So the total reactivity can still increase. And the C10 hydroperoxides can also be oxidized to the second generation product, C10 ketones. And both types of species can be oxidized to multifunctional species. And this type of species can survive more than a week of photochemical aging. And during this aging, they undergo fragmentation through organic photolysis and R2 self or cross reactions to produce many highly oxidized C1 and C2 species and some larger species. And finally, everything is oxidized to CO or formic acid before going to CO2. We also investigated the composition of these multifunctional species. We calculated the average functional group number per carbon atom from different functional groups. We can see in this plot, at lower ages, multifunctional species are mostly C10 dihydroperoxides and hydroxy ketones. And at higher ages, they are more diversely functionalized because of the chemical processing of organic photolysis and R2 plus R2. With the GECKO output, we can also calculate OH and HOX recycling ratios. I think they are important quantities in atmospheric oxidation capacity research. OH or HOX recycling ratio is the ratio of the number of OH or HOX produced per OH consumed in organic reactions. For this, decane oxidation results at lower age, OH is recycled through the conversion between hydroperoxide and ketone. At higher age, HO2 is mainly produced during multifunctional species fragmentation and C1 and C2 species oxidation. So at extremely high ages, OH where there is only CO and CO2, OH recycling ratio should drop to 0, while a HOX recycling ratio increases to unity. Now I've finished discussing the results of decane. Now let's look at the results for an aromatic m-xylene oxidation. It has a slightly higher OH reactivity peak at slightly lower age because m-xylene reacts with OH slightly more rapidly than decane. And it has new types of OHR contributors, such as aromatic species and unsaturated aliphatic species. And the latter category is highly reactive. We can find in this scheme the channel for aromatics and oxygenated alkenes, which are unsaturated aliphatic species. If we look at the composition of saturated multifunctional species in meta-xylene oxidation, we can find it's much more diverse compared to Decane oxidation. Because of the diverse reaction pathways shown here, and it's more oxidized because the multiple additions of O2 to the ring are generally very fast. But this scheme is not complete. Even we made major update to the MCM version, because there are several loops in the mechanism. For example, this one, and R2 reacts with HO2 to form hydroperoxide. Then it can react with OH to convert back to the R2. This interconversion within a loop is usually fast and faster than its exit channel. If we can't find some slow exit channel for the loop, the turnover number of the loop can be significantly artificially high. And we will see examples of this later. Now let's look at the oxidation of an alkene, which is isoprene. At high ages, the OHRVOC is very low. So I also show the fractional contribution of different species to the total OHRVOC below. And the most apparent difference in isoprene oxidation shown here is it doesn't have an OHR peak. Isoprene oxidation mechanism is relatively well known. We can easily find the oxidation chain for it, starting from isoprene and to isoprene-derived hydroxy-hydroperoxide, or isopo. Then isoprene-derived epoxydiol, or epox, then other saturated multifunctional species till CO2. In terms of absolute reactivity, isoprene is actually more reactive than isopo because it has one more CC double bond. And isopo is more reactive than epox because the latter doesn't have any double bond. So during the oxidation, the total attractivity always decreases. And the functionalities in saturated multifunctional species in isoprene oxidation are also diverse because in the mechanism, there are a lot of internal shifts of atoms and groups that can diversify the functionalities. And in this plot, we can find the major role of epox and its derivatives, especially here around 3 times 10 to the 10 molecule per cubic centimeter times second. We can easily find the contribution from one epoxy group and two hydroxy groups from epoxy. And the oxidation mechanism of isoprene in GECKO is not complete either, especially at very high ages when everything is oxidized to CO2 except for some multifunctional species that are left as dead end, because the core mechanism for isoprene is taken from MCM 3.3.1. And MCM doesn't consider extremely high ages. So this species doesn't have exit channel. But we can fix this problem by sending this dead-end species into the GECKO generator. Then everything should be oxidized to CO2. After discussing these different types of species, we can find a common oxidation chain for their oxidation mechanism. That is a precursor to first generation product, then maybe second generation products, then saturated multifunctional species, and fragmentation products, and finally CO and CO2. For Decane, the first few steps are Decane, C10 hydroperoxide, and C10 ketones. For m-xylene, it's precursor, oxygenated alkenes, maybe one more step of oxygenated alkenes. And for isoprene, it's isoprene, isopool, epox. And after that, the evolution is very similar. So this is a qualitative result. Based on that, if we want to find a more quantitative trend, first we should reduce the impact of this different size of precursors. So we calculated OH reactivity per initial carbon atoms. And here's the result. For different precursors, their OH reactivity per carbon atom can be orders of magnitude different. But once saturated multifunctional species are formed, OHR per C atom converges. And OHR per C atom, or we can say rate coefficient with OH per C atom is about 1 to 2 times 10 to the minus 12 cubic centimeter per atom per second. This is a typical average of CH2 group carbon atoms in CH2 groups and in oxygenated groups. And after this convergence, OHR per C atom for all precursors follows a similar decay. And we know OHR per C atom for the precursors, so we can make parameterizations for the whole evolution for lumped models. If we integrate the OHR per C atom over the whole course of oxidation till CO2, we can get the number of OH consumed per C atom for the whole oxidation course. And the result is here. But this plot has two issues. One is the oxidation is incomplete. Almost every carbon atom should react with OH once as CO before they go to CO2. So for isoprene and decane, the value should be close to 3. And we can also see a large contribution from C8, H10O3, or hydroxy metaxylenol in the metaxylene case. But this is actually an artifact due to the mechanism incompleteness, because this species is involved in a loop, and I think we have some missing exit channel for that loop, and the turnover number for the loop is artificially high. That's why this contribution is huge. To explain the roughly three OH molecules consumed per C atom, we can simply attribute them to the carbon oxidation state change due to OH oxidation. Each OH oxidation leads to an increase in carbon oxidation states by 2, or in more detail, by 1, through the direct reaction with OH, and by another one through the reaction with O2. So about 3 OH oxidations are needed for carbon oxidation state to increase from -2, typically in hydrocarbon precursors, to +4 in CO2. Now I've finished discussions about ambient cases. Now let's look at different environments. First, it's chamber. Chamber without wall is very similar to the atmosphere because they have similar UV range, similar OH concentration, and they don't have other perturbations. But chamber with wall is substantially different. In this decane oxidation case, the C10 multifunctional species in chamber suffer near complete wall loss. And this makes the OHR peak in the ambient case disappear. And the small fraction of multifunctional species that survive at high age are actually those with fewer carbon atoms. And chamber walls can significantly hinder the gas phase chemistry at high ages because almost all multifunctional species are adsorbed to the wall. These results seem to be surprising, but we have confidence in it because we use the chamber wall loss parameterization from well-known published results. And chamber wall can even serve as OVOC source at very high age. This no wall-to-wall ratio for product OH reactivity can be even less than 1 at very high ages, which is a sign of wall releasing OH reactants back to the gas phase. Now we look at the OFR. It can also have deviations from the atmosphere. We look at this OFR case with strong water vapor photolysis. at high relative humidity and lamp setting. We can see the one big difference is the suppression of products at low ages. And the other is less efficient fragmentation at high ages compared to the ambient case. Let's look at the first difference. It's actually due to the accumulation of R2, which sounds surprising, but let's look at it in detail. In OFR, because of its very high Hawks concentration, we can assume R2's main fate is its reaction with HO2, and here is a typical rate coefficient. Then the time scale for R2 to reach steady state in OFR is about 1 over the product of this coefficient and HO2 concentration. Then OH exposure reached during this time is about 1 over the rate coefficient times the ratio between OH and HO2. In the case of strong water vapor photolysis, this ratio can be close to 1 because of this reaction producing OH and HO2 at 1-to-1 ratio. So OH exposure can reach greater than 10 to the 11th molecule per cubic centimeter times second, even before an R2 steady state is reached. So R2 is accumulated at early stage of oxidation. Actually, more than 10% of total carbon is in the form of decyl proxy radical at the OHR peak. But this problem only happens when water vapor photolysis is strong. If water vapor photolysis is not so strong, the OFR case can be very close to the ambient case. And the other problem, inefficient fragmentation of multifunctional species, is caused by inefficient organic photolysis in OFR. And this is a known problem of OFR. In our earlier paper, we showed at very high equivalent age, organic photolysis in OFR is orders of magnitude higher than order of magnitude lower. I'm sorry, lower than ambient photolysis. Now we can understand the difference in the composition of multifunctional species in the ambient and chamber and OFR cases. OFR lacks efficient organic photolysis to diversify functionalities at high ages, and chamber walls significantly impede the chemistry of multifunctional species because most of them are adsorbed to the wall. I just mentioned lack of organic photolysis is a problem in OFR. Can we deal with this problem by adding more organic photolysis? For example, chamber lights? The simple answer is no. Adding 5 times chamber lights makes little difference in terms of the max fractional contribution from the multifunctional species in isoprene oxidation. If we want to make a significant difference, I'm sorry. The chamber lights would be needed. Chamber light with thousands of times stronger would be needed, but this is obviously very unrealistic. To summarize, we found a common oxidation chain to explain different types of precursors for the oxidation. And this can lead to similar reactivity per carbon atom evolution, starting from saturated multifunctional species. And in chamber, there can be substantial VOC wall losses for medium-sized precursors or larger ones. This can lead to qualitatively different results. In the OFR, R2 can be accumulated at lower ages when water vapor photolysis is very strong. And OFR lacks efficient organic photolysis at high ages. That's all I want to talk about today, and I'm happy to take any questions.
Thank you, Zhe. You have done a lot of work here. It's difficult to digest, but let's go for questions. If you have questions, please go ahead and unmute yourself and ask the question. Is there any question here in the seminar? Or you can also write the question and I can read it. Are there any questions? Zhe, I just have a quick question. It's not really a question. Can you please expand why is there a lack of efficiency in organic photolysis in the OFR?
I
mean, well, yeah.
Because I think this is in the relative terms. If we just consider the UV fluxes in OFR, it's not that weak, but in OFR, the photons are very energetic. They are at 185 and 254 nanometers. They create a lot of OH. So to reach a certain OH exposure or equivalent photochemical aging, the reactants, the UV photons, the reactants receive or see in OFR is very low compared to the atmosphere, because in the atmosphere, the OH concentration is very low. So to reach a certain photochemical aging, it should wait for a long time. And during this time, ambient photolysis can undergo to a significant extent.
Okay. And is there any modification you can do in the OFR? Or is there someone working on that or not?
We can modify the lights, but as I show here, it's very hard to make up the ambient photolysis OFR really needs experimentally, because in OFR, the photochemical age is very, very high. For example, days or weeks, and the residence time of OFR is just minutes. So you really can't do photolysis, ambient photolysis for days or weeks just during a time of 3 or 5 minutes in the lab. It's almost impossible.
Okay. There is a question here in the chat from Mary Bart. In the PBL, I will expect the hydroxy peroxides with high solubility to dry deposit onto vegetation. You can read it if you want to. Will you expect ambient OHR to change significantly because of dry deposition, similar to wall loss experiments?
Yes. Yes, in this case, the ambient case in PBL would be more similar to the chamber case with wall loss. But we didn't consider to that technical detailed level.
Okay. Are there more questions? If there are no more questions, I really appreciate it, Zhe, that you gave the seminar today.
Thank you.
Yeah, thank you. And I think you are collaborating here with some guys, Alenka. So,
yes,
right?
with Julia Lee Taylor and John Orlando.
Okay. Okay, it will be nice to have you here at some point.
Thanks.
So we can give you a tour or something here. Okay, everyone, thanks for joining today. Thanks, Zhe, again. Bye, everyone. Bye, Zhe.
Bye.
Bye-bye.